potential difference between 2 points in an electric field. Suppose there are 2 points in an electric field, and we want to calculate potential difference at a point. Potential difference may be defined as the amount of work done. Suppose I have a charge. Which is kept at point O. This is source charge. And I want to calculate potential difference between 2 points. What are those 2 points? Let me explain you. Suppose there is a point B, and there is a charge plus Q naught, and there is a charge plus Q naught. This charge is called test charge. Now consider that I have a source charge. Consider that I have a charge which is located at this point O. Okay, so consider that I have a charge which is located at this point O. So that charge is Q. Now if I have another charge Q naught which is at a point A, so I have a source charge. I have a charge Q which is located at point O. This is positive charge, and positive charge radiates out electric field. So because of this charge, an electric field will exist at point B. So what will be the direction of electric field at point B? Direction of electric field will be like this. It will be away from the positive charge. So this is the direction of electric field. I have studied it in chapter number 1 that direction of electric field is always away from a positive charge. Now if I have a test charge Q naught, and if I want to bring this test charge at this point B, then electric field's direction is in this direction, and I am moving this test charge against the direction of electric field. That means I am moving this test charge Q naught against the electrostatic forces. So work done required to move a test charge against the electrostatic forces between 2 points is called potential difference. Work done required to move this test charge Q naught from point A to point B against the direction of electrostatic force. This is called electric potential. Is this clear to you? Is the definition clear to you?
Can you explain again?
Okay, wait. What is the direction of electrostatic force? The direction of electrostatic force as well as electric field is away from the positive charge. I have a positive charge Q which is kept here. So because of this positive charge Q, the direction of electric field or electrostatic force, it will be in this direction. Now I am moving another test charge Q naught. From this point to this point. So I am moving this test charge Q naught in this direction. That is, I am moving it against the electrostatic force, in the opposite direction of electrostatic force. So the work done which this charge do from moving from this point to this point, that work done is called electric potential. Is this clear? Work done, suppose electric force is in this direction. And I have a test charge Q naught in my hand. So I am moving it against electrostatic force. Electrostatic force is in this direction, and I am moving it against the electrostatic force. So the work done is called work done in moving this test charge against the electrostatic force. That is called electric potential.
So you're like pushing it against the repelling forces.
Sorry?
But they both are like positive charges.
Yeah, they both are positive charges. They both are positive charges.
Always.
Always, always, always.
Okay, so
Okay,
then there
and
will be positive charges and you're pushing them against the electric field and the
yes,
repelling of both charges.
yes. Then that work done is called electrostatic potential. Okay,
Okay.
okay, Anusha, there is light is not there at this time. I I think you are sitting in dark. Please switch on the
Yeah,
light.
but I am the second last
Um,
I
okay,
will ask
okay, no problem. So V is equal to, we represent potential difference by the term V. So V is equal to VB minus VA. VB minus VA. VB minus VA means that the electric potential at point B and electric potential at point A. If I take the difference of both the electric potentials, then it will come out to be the potential difference. This is called potential difference. Okay. There is a small difference between potential. There is a small difference between electric potential and potential difference. What is the difference? Look, if I bring if I bring this test charge, if I bring this test charge from from infinity, if I bring this test charge from infinity and locate this charge at point A, then the work done in bringing a charge from infinity to a point in an electric field, this is called electric potential. Now I am bringing a test charge. Now I am bringing a test charge from infinity to point A. This is called electric potential. This is called electric potential of locating the charge at point A. This is called electric potential of A at point A. Now, if I bring the same charge, from infinity and locate it on point B, then this is called the electric potential at point B. The work done is called electric potential at point B. So this is another method. This is another way of defining potential difference. So work done in bringing test charge from infinity to point A, this is called VA. Work done in bringing the test charge from infinity to point B, this is called VB, and the difference of both these potentials is called potential difference. Is this clear? Okay. Now, SI unit of potential difference is, okay, this is defined as work done in moving the test charge from A to B, WAB upon Q naught. Work done per unit charge is called electric potential. And sometimes in a common language, we call electric potential and potential difference as the same terms. Okay, so electric potential, the SI unit of electric potential or potential difference, it is joule per coulomb. SI unit of electric potential is joule per coulomb. Joule per coulomb, J C की power -1 or volts. V. Now electric potential.
So electric potential is like the work done to bring like the charge from infinity to the test charge and the test charge to point B and potential difference is the difference between them.
Yeah, potential difference is the difference between them. Actually, there are two methods of defining potential difference. First method is this: कि work done in moving a test charge from point A to point B, but that work done should be against the electrostatic forces. So electrostatic forces in this direction, because this is positive charge Q, and Q radiates out electric field outwards it. So work done in moving charge from A to B, this is called this is called potential difference. And another method of defining this is that if I bring a test charge from infinity to point A, so work done in bringing test charge from infinity to point A minus work done in bringing the test charge from infinity to point B. The difference between them is also called potential difference. Okay. Now, we will define electric potential. Electric potential. What is this electric potential? Electric potential at a point in an electric field is the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic forces. This is again the same thing which I have discussed right now. Suppose I have a source charge like this. Q, and there is a point A, and from infinity I am bringing a test charge Q naught. Now a test charge Q naught, and I am locating it at point A. Okay, so the work done in bringing this test charge from infinity to point A, this is called electric potential. So electric potential is equal to work done per unit charge. Mathematically, electric potential is equal to work done upon charge. All right, is this clear to you?
Yeah.
Okay. Next topic is electric potential due to a point charge. So this time I have sent you chapter number 2 and chapter number 3. So chapter 1 I have already shared it with you, and chapter 2 and 3 I have shared today. So you can take the printouts of all these 3 chapters. Okay. Try to study by hard copy only. Electric potential due to a point charge. Consider a positive point charge small q placed at the origin O. So let us consider a positive point charge small q placed at the origin O. We wish to calculate its electric potential at a point capital P at distance small r from it as shown. So let us consider a positive point charge small q. So we have considered a positive charge small q which is placed at the origin O. It is placed at origin O, and let us draw a straight line like this, and after that a dotted line like this, and then let us mark 3 points. This is point A, this is point B, and this is point P, and the distance between O and P is R. Distance between O and P is R. Distance between O and A is X. Distance between O and A is x. Distance between A and B is dx. Okay, and write q naught here, write infinity here. Now let me talk about electrostatic force. Let me first talk about electrostatic force. What is this electrostatic force? Electrostatic force is electric field. It is force due to the electric field. So what happens? I have a positive charge, so it radiates out electric field. It radiates out electric field. Like if I am talking about this line, then electric field will be in this direction, because electric field always goes out of the positive charge. Electric field always comes inside the negative charge. So if I have a positive charge, then electric field will always be outside this positive charge. So what will be the direction of electrostatic force? The direction of electrostatic force will be like this. Direction of electrostatic force will be like this, F. So this is electrostatic force. Is this force is clear to you, Anusha? Tell me. So at point A also it is in this direction, at point B also it is in this direction, at point P it is in this direction. Actually this electrostatic force is because of this charge. Understand? So this positive charge always...
What about the test charge?
Sorry?
What about you said electric potential was like you're taking a test.
No.
Test
First of all,
charge.
don't. First of all, you don't need to focus. Do not focus on this test charge Q naught. First of all, I am focusing on this charge Q. This is called source charge. Source charge means the charge which I have already. So I already have this charge Q, and what will be the direction of electrostatic force? I will come on electric potential later. First of all, understand what will be the direction of electrostatic force. It will be like this at every point on this line, because of this positive charge radiates out electric field. So the direction of electric field is the direction of electrostatic force. Now I am coming on test charge. Now I have a test charge Q naught, and I have placed this test charge from point A, and I am moving this test charge to point B. Okay, so I am moving it in this direction. Because to calculate electric potential, I have to move test charge against the electrostatic force. Electrostatic force is in this direction, so I have to move test charge Q naught in this direction. Is this clear to you?
Yes.
Okay, now try to understand. We are on page number 2. And on page number 2, on the top of page number 2, I have drawn this diagram, and after that what is written? Suppose a test charge Q naught is placed at point A at distance small x from O. Suppose a test charge Q naught is placed at point A at distance x from point O. By Coulomb's law, the electrostatic force acting on charge Q naught is... Electrostatic force acting on charge Q naught is... Is this clear?
Yes.
By Coulomb's law, F is equal to 1 upon 4 pi epsilon naught Q1 Q2. So this time Q1 is Q and Q2 is Q naught. So 1 upon 4 pi epsilon naught Q naught upon distance between Q and Q naught is x upon x square. Okay, and now I am moving this test charge from point A to B. So what is the distance between A and B? It is dx. It is very small distance. So look, this is equation number 1. Now in your notes, the small amount of work done after equation number 1, I am reading out after equation number 1. So the small amount of work done in moving the test charge Q naught, from A to B through small displacement dx vector, it is small amount of work done is dw is equal to F vector dot dx vector. ठीक है. What is work done? Work done is always f vector dot dx vector. It is always dot product. It is always scalar product or dot product between the two vectors, between force and displacement. So this is f vector dot dx vector. Now what is the direction between f and dx? Look, f is in this direction, f vector is in this direction, and dx vector is in this direction. So f vector is in this direction, dx vector is in this direction. So f vector is in this direction and dx vector is in this direction. So what is the angle between f vector and dx vector? It is 180 degree. 180 degree. So what is f vector dot dx vector? It is a vector dot b vector is a b cos theta. Similarly, f vector dot dx vector is f dx cos theta. F dx cos theta. What is theta? 180 degree. So dw means small amount of work done is equal to f dx. And what is cos 180? Cos 180 is minus 1. So this is minus f dx. dw is minus f dx. If it is clear till now, then I will move further.
Yes.
Okay. Now, so the total amount of work done. So the total work done in moving the charge q naught from infinity to the point P will be. So total amount of work done will be, if I have a small amount of work done dw and I want to calculate total amount of work done, then w is equal to integration of dw. W is equal to integration of dw. Okay. Now integration, what is dw? dw is minus f dx. Okay. Now dx, x is variable. The term which is written with small d is called variable term. So now x is the variable and x is moving from where to where? Look, x is moving. I am going to bring this test charge not between these 2 points. Actually, I want to bring it from infinity to point B. I want to bring it from infinity to point B. So what will be my initial position? Initial position will be infinity. And what will be the final position? I want to bring it to position R. So infinity to R. Is this clear to you? I write initial limit, lower limit here and upper limit here. So I am bringing this test charge from infinity. Yani ki if I take infinity to be the distance, then what will be this x? X will be equal to infinity. And if I am bringing this charge q naught from infinity to point P, then what is the distance between O and P? It is R. Means x becomes equal to R. Is this clear to you?
Yes.
Okay, so from infinity to R, now this is negative sign. I can take out this negative sign out of integration. Minus integration infinity to R. What is f? F is 1 upon 4 pi epsilon naught q naught upon x square. 1 upon 4 pi epsilon naught q naught upon x square into dx. Now tell me, is this clear?
Yes.
All right. Now, what is variable here? The term which is written with small d. The term which is written with small d is variable. What is written with small d? It is x. So x is variable. Rest all other terms will be treated as constant. Okay. So if you have written it till here, then shall I move on to the next slide?
Yeah, Q and Q naught are constant here.
Yes, q and q naught is constant. 1 upon 4 pi epsilon naught is also a constant. Actually, everything except x will be treated as constant. Only x is variable and every other thing will be treated as a constant. Understood?
Okay, so then
I will take out all the things, all the terms except this x square out of this integration. Okay, so now I'm moving on to the next slide.
upon infinity is 0.
Yes.
So 0 minus 1 by r
Yes.
minus into 1 by r. I took minus completely outside, so it will be minus q naught by 4 by epsilon into 1 by r.
Yes.
So is that like my final thing, or do I have to substitute something?
Nothing. Look, you are understanding it. You are understanding it in the right way. This is q naught and 1 upon 4 pi epsilon naught, and q naught will come out of integration. It will be like this. W is equal to minus 1 upon 4 pi epsilon naught q naught integration 1 upon x square. We can write 1 upon x square like x to the power minus 2 from infinity to r. W is equal to minus 1 upon 4 pi epsilon naught q naught. Now how will I integrate x to the power minus 2? X to the power minus 2 plus 1 upon minus 2 plus 1. Lower limit is infinity, upper limit is r. Minus 1 upon 4 pi epsilon naught q naught x to the power minus 1 upon minus 1 infinity to r. Now I can take out this minus 1 out of this box. Okay, so minus 1, if I take it out of this box, then minus 1 divided by minus 1 will become plus 1. So it will be 1 upon 4 pi epsilon naught q naught, and x to the power minus 1 means 1 upon x, 1 upon x infinity to r. Now 1 upon 4 pi epsilon naught q naught. First of all, I have to keep this r at the place of variable. So 1 upon r minus upper limit. I substitute upper limit first, then subtract it, then subtraction sign, and 1 upon infinity. What is 1 upon infinity? Please remember it. 1 upon 0 is equal to infinity, and 1 upon infinity is equal to 0. So this is 0. So what I have, W is equal to 1 upon 4 pi epsilon naught q naught into 1 upon r, means q naught upon r. Is this clear to you?
Yeah.
Okay. Since electric potential V is equal to W upon q naught, electric potential V is equal to W upon q naught. V is equal to 1 upon q naught into W, 1 upon q naught into what is W? 1 upon 4 pi epsilon naught q naught upon r. Cancel q naught by q naught. So V is equal to 1 upon 4 pi epsilon naught q upon r. This is electric potential due to a point charge small q at a distance small r from it. Is this clear to you?
Yes.
Okay. Now just give me 1 minute, I am coming. Wait for 1 minute. Okay, now in the same manner as I have discussed in chapter electric charges and fields, in the same way, the next topic is on page number 3. We have electric potential due to a dipole. What is dipole? Two equal and opposite point charges separated by a small distance makes an electric dipole. So electric potential due to a dipole. Electric potential due to a dipole. First, electric potential at an axial point of a dipole. Electric potential at an axial point, electric potential at an axial point of a dipole. Now, consider an electric dipole consisting of 2 point charges minus q and plus q and separated by distance 2a. Let P be a point on the axis of the dipole at a distance small r from its center O. Now, come on to page number 4 of the notes. Come on to page number 4 of the notes. So, let us draw an electric dipole like this. This is point O, this is point A, this is point B, minus Q plus Q, minus Q plus Q. Center of the dipole is O. So Anusha, this is an electric dipole. This is not a new thing for you. You have done it in chapter number 1 also. This is an electric dipole. Now, I want to calculate, this time I am not going to calculate electric field. This time I am going to calculate electric potential at a distance small r at an axial point of this dipole. Axial point means a point which lies on the axis of this dipole. So, let us consider that point to be P, small p. This is point P. I want to calculate electric potential at point P. So the distance between the center of this dipole and this point P is small r. Small r. Anusha, wait for a moment. Okay, am I audible to you? Hello, Anusha, am I audible to you?
Yes.
Okay. Okay. So from point O, I want to calculate electric potential at point P. So what is the distance between point O and P, we always consider it as small r. Now, sorry, sorry, this is small a, this is small a, and this distance is also small a. Now, electric potential at point P due to the dipole is, now you have to understand one thing. There is one difference here in electric potential and electric field. In electric field, actually electric field was a vector quantity, but electric potential is not a vector quantity, it is a scalar quantity. So in electric potential, whenever I have to calculate electric potential, then I do not take the magnitude of charge, q and minus q. We always take the sign also, we always consider sign also. So if I want to calculate electric potential due to this charge minus q, then I will consider it to be minus q only. But in electric field and electric force, we take only the magnitudes. Here we will take the sign also, electric potential. This is the main difference between electric force, electric field and electric potential, because electric force was a vector quantity, electric field was a vector quantity, but electric potential is a scalar quantity. So in electric potential we consider sign also. Okay, so electric potential at point P due to the dipole is, right, electric potential at point P, electric potential at point P due to the dipole is, due to the dipole is V is equal to V1 plus V2. V is equal to V1. V1 means electric potential due to this minus q charge. So it will be 1 upon 4 pi epsilon naught. What is this minus q? This is a point charge. So I have derived this formula that electric potential due to a point charge is 1 upon 4 pi epsilon naught q upon r. 1 upon 4 pi epsilon naught q upon r. So 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught minus q upon what is the distance between minus q and this point P. I want to calculate electric potential at point P. So what is the total distance? It is r plus a. So q upon r plus a, plus 1 upon 4 pi epsilon naught. What is the electric potential due to this charge q? Q upon this distance is r and this is a. So what is this distance? This is r minus a. Q upon r minus a. Now q upon 4 pi epsilon naught, we can take it out as common. Q upon 4 pi epsilon. Anusha, is this clear to you till now?
Yes.
Is there any doubt?
Can you explain that?
No problem. No problem. Whenever you have doubt, you have to ask it again and again. All right. So V1 is the electric potential due to charge minus q. So what will be the electric potential at point P due to this charge minus q? 1 upon 4 pi epsilon naught, as per this formula, 1 upon 4 pi epsilon naught q upon r. So 1 upon 4 pi epsilon naught minus q upon distance. Distance is r plus a. So distance is r plus a as per this formula. Next, electric potential V2, electric potential due to charge plus q. 1 upon 4 pi epsilon naught charge is plus q upon distance between plus q and p. This is r minus a. So this is r minus a. And we are going to add up these two potentials. So the total potential due to this dipole at point P will come. Understand?
Yes.
Okay. Now, I will take it out. Q upon 4 pi epsilon naught common. Q upon 4 pi epsilon naught is common. Now, what we are left with, it is minus 1 upon r plus a plus 1 upon r minus a. Minus 1 upon r plus a plus 1 upon r minus a. V is equal to Q upon 4 pi epsilon naught. Now, LCM. When we have different terms in the denominator, then to find out LCM, we simply multiply these two terms. So, what I will get in the denominator here, r plus a into r minus a. Now, r minus a into minus 1 is minus r minus a. R plus a into 1 is plus r plus a. If you have noted down till here, then I will move on to the next slide.
Last one.
Note it down, note it down. Don't worry. Done?
Yes.
Okay. Now, on to the next slide. We have V is equal to Q upon 4 pi epsilon naught. V is equal to Q upon 4 pi epsilon naught minus r minus minus plus a minus r plus a minus r plus a plus r plus a plus r plus a upon r plus a into r minus a is r square minus a square. R square minus a square plus r minus r cancel out. V is equal to 1 upon 4 pi epsilon naught, and I am taking this q inside the bracket. That's why I have taken 1 here, and I will take this q inside the bracket. A plus a is 2a. A plus a is 2a. So 1 upon 4 pi epsilon naught 1 upon 4 pi epsilon naught q multiplied by 2a upon r square minus a square. Why I have taken this inside? Q into 2a is dipole moment. So I will write P here. P is dipole moment. So V is equal to 1 upon 4 pi epsilon naught P upon r square minus a square. And as I know that this distance r is very greater than the dipole length 2a. So r is very greater than a. Look, for a short dipole, r square, for a short dipole, r is very greater than a. So r square is further very greater than a square. So a square can be neglected. One upon 4 pi epsilon naught P upon r square. V is equal to 1 upon 4 pi epsilon naught P upon r square. Is this clear? Okay. Next, electric potential at an equatorial point of a dipole. Electric potential at an equatorial point of a dipole. Electric potential at an equatorial point of a dipole. Now, consider an electric dipole consisting of charges minus q and plus q and separated by distance 2a. Let capital P be a point on the perpendicular bisector of the dipole at distance small r from its center O. Perpendicular bisector, equatorial point always lie on the perpendicular bisector of the dipole. So let us draw the figure again. Point A, point B, and I have a charge minus q here and a charge plus q here. Minus q and plus q. Center is O. Center is O. What is the length of the dipole? It is 2a. So it is A and it is A. And I am considering a point on the equatorial point. Equatorial point is like this on the perpendicular bisector. On the perpendicular bisector. So wait, Anusha, just for one more moment. At an equatorial point. So this is an equatorial point P. Equatorial point P. Now join this point by A like this, join this point by B like this. Now whenever I take a distance, whenever I consider a point, so I am considering point P, and from point O it is at a distance small r. It is at a distance, I consider the distance to be small r only. So by Pythagoras theorem, because it is at the perpendicular bisector, by Pythagoras theorem, what is this distance? This distance is under root r square plus a square. In the same way, what is this distance? This distance is also under root r square plus a square. Is the figure clear to you? Is it clear to you?
Yes, sir.
Okay. Now, electric potential at point P due to the dipole is, electric potential at point P due to the dipole is, at point P due to the dipole is V is equal to V1 plus V2. So V is equal to V1. What is V1? V1 is electric potential due to charge minus Q. So 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught minus Q upon under root, what is the distance between minus Q and P? Under root R square plus A square plus V2. 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught. What is the distance between this V2 is electric potential due to this charge plus Q. So what is the distance between plus Q and this point P? Under root R square plus A square. So Q upon under root R square plus A square. So this is a positive term and this is the same negative term. It will get cancelled out by this. So V is equal to 0. So electric potential at an equatorial point due to a dipole is always 0. Is this clear to you?
Yes.
Is this clear to you? Now, I wanted to cover the next topic also, but the next topic will take some time. So, let's do it. Let's finish it here only. I will do it at 9:30 p.m. Indian time tomorrow. Tomorrow is Saturday, na? So we will continue it tomorrow. Okay, Anisha? All the topics we have discussed today, all the topics are clear to you?
Yes.
Okay, okay. Then see you tomorrow.
Okay. Thank you so much. Have a good day.
Okay, same to you.